Okay, in this talk I will be addressing various things related to prime numbers, amongst others algorithms for integer factorization, primality tests, and prime sieves. Specifically, I will be talking about the sieve of Eratosthenes, primality tests, and integer factorization. Let's start with the sieve of Eratosthenes. The motivation behind it is that given a natural number n, to find all prime numbers less than or equal to n. The way you can do this in code is to generate a list of numbers from 2 to n and then declare some integer p, which we will set to 1. And then every iteration we are trying to find the first integer that's greater than the current p and filter out all the multiples of p. And at the end of the algorithm, we will simply return a list, and this list contains all integers that are prime from 2 to n. There's quite a few optimizations you can do here. Amongst others, you can actually segment the sieve, which means that instead of looking at the interval 2 to n at once, you're actually trying to sieve in blocks, which is perfect because you can access one block with relatively few cache line accesses at once, which is obviously much better in terms of memory and performance. Another optimization you can do is to limit the upper bound of the algorithm to the square root of n. What this does is that if you have a multiple of some number that's less than n, then its two factors are not going to be both greater than the square root of n. So if one factor is greater than the square root of n, the other factor is going to be less than the square root of n, meaning it's going to be filtered out anyway. So we can actually discard all the integers that are greater than the square root of n because these multiples will already have been filtered out. Next, we can discard numbers ahead of time, which simply means that if we know that any even integer is not a prime, we can get rid of it at compile time already, aside from 2 obviously, which is even but a prime. And there's even more things you can do. In fact, there's faster performing sieves, but I'll not go into detail in this presentation. Next, we have primality tests, and what's the actual goal we're trying to achieve is to check if a natural number n is prime. The simplest thing you can do is trial division, which means that we're given an interval from 2 to n, and we're simply enumerating all x and checking if x divides n. And if it happens to actually divide n, then we know that n is not prime, meaning it's a composite number. A faster test, or a more known test, is the Fermat primality test. It's based on Fermat's little theorem, which states that given an integer a and prime p, then a to the p is congruent to a modulo p, or a to the p minus a is a multiple of p. Similarly, if p and a are co-prime to each other, then a to the p minus 1 is congruent to 1 modulo p, which means that a to the p minus 1 is a multiple of p. What you can actually do with this statement now, with this theorem now, is construct a test which basically picks out a random base a for possible prime number n, and we're checking if Fermat's little theorem holds. The way we do this is we are checking if n divides a to the n minus 1 minus 1. And if it doesn't, then we know that n is not prime, it's composite, and base a is a Fermat witness for compositeness of n. Otherwise, you might be quick to think that if the statement is true, then n is prime. However, that is incorrect because there's a type of number that we'll encounter in a minute where Fermat's little theorem holds even if our n is composite, namely Fermat pseudoprimes or Fermat liars. And a Fermat pseudoprime is some composite m for which any base, or for some base a, Fermat's little theorem holds. And we say that m is a Fermat pseudoprime in base a. There's a relatively easy fix, obviously, which is because most of these Fermat pseudoprimes are only pseudoprimes in some specific bases. You can basically go through every possible base A until you encounter a base where m is not actually a Fermat liar, meaning you've determined that it's composite. In practice, obviously, this is really slow. In fact, it's no better than just doing trial division. So in practice, you would only test some select few bases, and then there's a high chance you're actually determining that M is composite after only a few iterations. However, that's not really a bulletproof fix because we have another type of number. They are called Carmichael numbers, and a Carmichael number is a composite number p such that b to the p minus 1 is congruent to 1 modulo p for all integers b. What this means is that even if we actually cycle through all possible bases a, like an example I just suggested a second ago, that there are some composite numbers where this is practically irrelevant because Fermat's theorem holds for any base b in this case. A more common or test that's used today is the Miller-Rabin primality test. And what it does is that we first of all represent p minus 1, where p is some prime, as 2 to the s times d, where d is some odd positive integer and s is some positive integer. The reason we can do this is that p is guaranteed to be an odd number aside from the number 2, but we're not expecting it to is going to be an input for the algorithm, so we can simply discard that. So p minus 1 is going to be even for sure. We then extract all the powers of 2 from this even number, and what's left after doing this process is some odd d, which we're just going to multiply this with. So this is just a way to factor p minus 1. The next idea this test relies on is that p is a prime number if and only if the roots of x squared are plus or minus 1 for in modulo p. And in order to actually confirm this test, we must also confirm that an nth degree polynomial only has n roots at most, because this way we know that there's no other solution for x squared where p might actually be prime. So that way we can't have some other integer where x squared is 1 modulo p, and that this way we actually have a very reliable way of checking if our p is a prime number. The way we go about doing this is by first of all assuming that a polynomial f of x over some Galois field set p of degree n has at most n roots. Next, we're simply going to prove this by induction. We are setting up a polynomial y is a times x plus b, and this obviously has one unique solution, which is minus b over a. And we then assume that we have some polynomial f of x with a degree of at least 1, which has one root a, x minus a. In this case, this root is just positive a. And then another polynomial, g of x, which has at most n minus 1 solutions, because it's a polynomial of degree n minus 1. Now the solutions of g of x are, again, one root a or b, in this case, whatever we want to call it, and then another polynomial h of x, which is of degree n minus 2. And by induction, we can then say that because we are trying to find the roots of this polynomial, modulo p, that p divides either x minus a or g of x, and because g of x has at most n minus 1 roots and a is 1 root, we have at most n roots. Next, what we can do is simply substitute in our new expression for p minus 1 into Fermat's little theorem, and we can factorize this expression even further with the binomial formula, and we can keep going until we reach an odd exponent, and the last two terms or factors will be these ones, and the full expression will look something like this. We have s plus 1 factors on the left, and now there's two cases that can happen, and exactly one of them has to actually happen so that p is prime. So firstly, either a to the d is 1 modulo p, which means that this factor right here is a multiple of p, because if you know the zero product property, that means that at least one of these factors has to be 0, so that we get a 0 mod p result here. And the second thing that can happen is that some of these factors, most of them you can't even see because they're hidden, but some a to the 2 to some power of 2 times d has to be -1. And now you might wonder how this actually relates to the square roots of x squared modulo p. Well, the reason is that if we have a to the d minus 1, if this actually ends up being a root, then that means that all subsequent factors have to end up being 1. And similarly, if at some point, if this doesn't end up being 1, then at some point in the future, one of these factors has to end up being -1, because -1 squared is 1. So the last term in the sequence that is not 1, if you go at it from the highest order term, has to be -1. So if p wasn't prime, and for some reason you would get a square root of 1 that's not -1 or 1, then you know that p is not a prime. Now the probability of success. Well, contrary to the Fermat test, we actually know that for a single random base, the chance of success is roughly 3/4, which is great because we can actually calculate for some base a, for how many times we're iterating, how high the chance of success is. So the chance of successfully determining whether we've found a prime or not. And on that occasion, I should actually note that the Miller-Rabin primality test doesn't actually prove whether a number is prime. If anything, it proves it's composite. However, we still know with a very high chance whether the number we're testing is prime or not. And in fact, you can go as far as making it deterministic by just checking multiple bases. And for a 32-bit integer, you would check these bases, namely 2, 3, 5, and 7. So if the conditions I've just proposed hold for all of these bases, then we've sort of proven, or we know for sure, that p is prime, or n is prime, whatever number we're testing basically. The reason this is true is because the first number that actually passes the test for all of these bases and is a composite number is far beyond the limit of a 32-bit integer. And you can obviously test even more bases and increase the determinism, so to speak. Next is integer factorization. When we are trying to factorize an integer, then we have some natural number n with two distinct prime factors, and we're trying to retrieve those given n. Again, you can do trial division. So you set up some array of prime factors, and you go up from 2 to the square root of n. You cycle through every possible factor and check if it divides the number that we're trying to factorize. At the end, if there's a prime remaining, so if n is greater than 1, then we know that that's a prime factor itself, and we can simply push it to the array. Well, the reason we're going to the square root of n and not to n itself, going up to the square root of n, not n itself, is because, again, like I mentioned in the Sylph of Eratosthenes, you can't have all prime factors of n be greater than the square root of n. So there's at least one factor that actually ends up being less than the square root of n, less than or equal to the square root of n, meaning you're fine, even if there's a factor that's greater than the square root of n. And at the end, of course, we are returning the array, and this array contains the prime factors of n. There's a simple optimization you could do here, and it's basically to skip multiples of numbers that we've already checked. For example, if we are factoring all the powers of 2 out of the number at first, then we can later on skip all multiples of 2 because we know we've already factored out all of these multiples anyway. And ideally, you would actually do this with the sieve of Eratosthenes, for example, which means you pre-compute all possible primes and then check each of those individually, which is actually quite useful for smaller integers, but obviously not feasible as your number approaches higher dimensions. The reason we call it wheel factorization is because if you imagine a wheel, and in the center of that wheel we have our number n, and then around the center we have our multiples of n. Each multiple actually approaches an outer layer of the circle. It's called wheel because of the shape, essentially. Then there's Fermat's factorization method. For any odd positive composite integer n equals p times q, we can represent it as the difference of squares. And that's basically the principle of Fermat's factorization method. If we happen to guess an a such that b squared is a square as well, then we know that we found the factors a plus b and a minus b of n, and this is just expanding this term right here. The way to implement this is to first of all determine an upper bound, we will call it a, and we set it to the ceiling of the square root of n. The reason we are doing this is quite obvious. First of all, ceiling is idempotent, meaning if a was an integer, it will remain an integer in case n is a perfect square. And otherwise, we are taking the ceiling because in our next step, when we compute b squared, we are trying to get a valid integer, positive integer. And then we check if b squared is actually a square by rounding it and then taking the square root of b squared. And if it's not, we just increase a, calculate this exact same thing again, and see if b squared is now a square. And at the end, obviously, you can return one of the factors, a plus b or a minus b. Next, we have Pollard's p-1 algorithm. And the concept of smooth numbers is pretty important in the context of this algorithm. We will denote the ith prime factor of a number with q sub I, and then the following definition follows. So a number x is b-smooth if q sub I divides x. For all q sub I that divide x, q sub I is less than b. And similarly, a number x is b power smooth if the prime powers are all less than or equal to our base b or b. For example, if x was 74, then its prime factors are 237. The number is 37 power smooth because all of its prime powers are less than or equal to 37, but it's obviously not 2 power smooth. With that in mind, we can now actually use this concept to factor our number. So Fermat's little theorem states that a to the p minus 1 to the k is congruent to 1 modulo p for coprime p and a. This is just a slight extension of the theorem I showed you earlier, but it's obvious why this still holds. And next we're going to substitute u for k times p minus 1. And now we can actually observe that a to the u minus 1 is a multiple of p. The reason this is true is because if we subtract 1 from here, then a to the u minus 1 is 0 mod p, and this means that p has to divide the greatest common divisor of a to the u minus 1, n. This is just substituting p times m in here and p times q in here, and we'll see that the p actually factors out. And this is always true, and in fact, most of the time, p is actually going to be the greatest common divisor anyway, unless there's the off chance that p and q both divide our a to the u minus 1, then the greatest common divisor is going to be n, and you would simply repeat the process. And the way we actually can get such a u that a to the u minus 1 is a multiple of p is that we first express the largest possible exponent a b power smooth number can have for some prime power. And It's very simple to calculate this. If you recall the definition I gave you earlier of p power smooth numbers, q to the q sub I to the r is less than or equal to b. So if you take the logarithm of both sides and then divide, you actually get this number. You then take the floor of it, so it's obviously a valid integer, and we will call it alpha I. And the largest possible b power smooth number is then given by pi from, well, the product of all prime numbers in the interval 1 to b and raised to the power of alpha I. So what we get is in most cases, a very big product of prime powers that are all less than or equal to b. The reason this is useful is because if you think about it, and if we actually go back to the previous slide, we want p minus 1 to be, well, p minus 1 can be a multiple. So u can be a multiple of p minus 1. And in order to increase our chances of actually encountering a multiple of p minus 1, we're trying to include as many small prime factors as possible. And that's why we choose such a big power smooth number, because, well, it will include many small prime factors, and our chances of encountering a multiple of p minus 1 increase. Lastly, we have Pollard's row algorithm, and the idea this algorithm is based on is that we take some arbitrary polynomial f of x modulo n. Often we simply choose this to be x squared plus c, where c is a parameter you can pick according to your use case, and then we construct a pseudo-random sequence. The reason it's pseudo-random is because it cycles, as you can see here, due to the modular operation that we apply on it, and the sequence is constructed that any x sub I is f applied I times to our starting value x sub 0. X sub 0 can also be chosen by the user accordingly. And next, we're going to observe x sub I modulo p. Obviously, we don't know p. P is the number we're trying to get, but there's still one observation we can make about it, namely that x sub I mod p cycles when there's two indices, s and t, that are equal in this x sub I mod p cycle. So when they're on the same position, even though they are different indices. And then we know that by rearranging this equation, so subtracting x sub t from both sides, we know that x sub t minus x sub s minus x sub t is a multiple of p. That again means that p divides the greatest common divisor of x sub s minus x sub t and n. The only case where this is not true is if this sequence, so x sub I mod p and x sub I, cycle at the same time, because that means the x sub s and x sub t in our original sequence will end up being on the same position, meaning that they'll have the same value as well. And I'd like to interject for a moment here and explain why I'm referring to position. Well, it's called row algorithm because if you look at the shape of the cycle, you can represent it in such a way that it looks like a row. That's why it's called row algorithm. And if both of these have the same value, x sub s and x sub t, in our original sequence, then the greatest common divisor is going to be n, because we have 0 and n here, meaning we are left with a GCD of n. The only question remaining now is how we actually go about finding the cycle, and there's many ways of doing this. One of them is Floyd's algorithm, which is quite popular because it's a form of a tortoise and hare algorithm. So you have one pointer that advances, or that is always trailing the other pointer. In this case, the tortoise pointer is always behind the hare pointer. And if a cycle occurs, they will eventually meet. And then we know, hey, a cycle occurred because there's no way they can actually be on the same position otherwise. And with that, I conclude my talk.